Today I'll be talking about the concept of an ECG. An ECG is a test that measures the electrical activity of the heart. The depolarization of the heart starts at the sinoatrial node and spreads rapidly to the AV node. At this point, the depolarization is delayed so that the blood can move from the atria to the ventricles. After this, depolarization occurs rapidly through the nerve fibers called the bundle of His. This bundle of nerves breaks off into a left bundle branch and a right bundle branch. Depolarization ends at the Purkinje fibers that spread the depolarization rate. The numbers on this diagram represent the time in fractions of a second, and you can see that the depolarization between the SA node and the AV node occurs rapidly. There is a large delay in the AV node from 0.4 to 0.16 seconds. We can also see the depolarization through the bundle of His is rapid. Next, I'm going to talk about what occurs during depolarization. At first, the SA node is more negative inside than it is on the outside. This represents the resting membrane potential, and the surface potential from one end of the cell to the other is 0. The rectangle represents the syncytium, where it is negatively charged on the inside and positively charged on the outside. As depolarization continues, there are negative charges moving in, and they are called the depolarization transmember. There is a rise in potential on the other end of the cell. At one point, there is an equal amount of positive and negative ions on the outside of the cell. This is where the cell reaches its maximum potential. Eventually, the potential will begin to decrease as more negative ions enter. When the cell has become completely depolarized, there is no potential difference. The cell is positively charged on the inside and negatively charged on the outside. Over the course of depolarization, the surface voltage changes and can be represented by this graph. The peak is when there is equal amount of negative and positive ions. The movement of the ions can be represented by this dipole model. The repolarization of the heart occurs the same way as depolarization, but it starts with the cell being positively charged on the inside and negatively charged on the outside. As positive ions move in, the surface charge decreases. When there are equal positive and negative ions, the surface voltage reaches its minimum. When there are more positively charged ions than negatively charged ions, the voltage begins to rise and move closer to 0. Once it has been completely recharged, there is no potential difference. The voltage can be graphed over time, and the minimum is where there is an equal amount of positive and negative ions. On the ECG waveform, there are different sections that can be read. The first part is the P wave, which shows the positive atria depolarization. This is when the SA and the AV node depolarize, and the PR interval shows the delay caused by the AV node. The QRS complex shows ventricular depolarization. It is fast through the bundle of His and is large. The T wave is the repolarization of the ventricles, and it is a positive deflection. The repolarization of the atria is not shown on the waveform. This image represents the dipole movement through the heart. The yellow arrows show the direction of the movement, and the size of the arrows represents the magnitude of the deflection. The P wave is the atria depolarizing. The Q wave is negative due to some of the Purkinje fibers firing at the apex of the heart. The R wave is showing the fast depolarization of a majority of the cells. The S wave is the negative wing, and the T wave is the repolarization from the apex to the base. In order to capture the ECG waveform, physicians need to connect leads to the body. This is an example of a 3-lead ECG, which is considered to be non-clinical. Originally, lead 1 was connected to the left arm, lead 2 was connected to the right arm, and lead 3 was connected to the left leg. Now the leads are placed on the chest, with lead 1 under the left clavicle, lead 2 under the right clavicle, and lead 3 under the ribs on the left side. This diagram shows how depolarization is captured. Lead 1 is connected to the positive terminal under the left clavicle and ends at the negative terminal under the right clavicle. The second lead is the biggest depolarization lead, which is the QRS wave. Lead 3 is connected from the positive terminal to the end of the second lead. From the triangle in the last diagram, we can obtain vectors. This is a vector representation of the 3-lead ECG, and it is 2-dimensional. In order for an ECG to be considered clinical, there needs to be 12 leads, and that would make the vectors 3-dimensional. This is an example of the waveforms collected by the 3 leads. The heights from the recordings can be used for vector analysis. If you only have 2 vectors, you can use them to predict the third. When things are not normal, the ECG waveform reflects this. The PR interval can be prolonged, or the QRS wave can be inverted. Both of these are signs that the heart is not pumping properly.